Hi guys, today we're going to be continuing from where we left off over a year ago, which was building the drivetrain frame. I extremely apologize for the fact that there was no audio in the last video. I know that probably made a lot of the parts of the video confusing, but I think if you just follow what's on screen, it shouldn't be too bad. Definitely just comment down on the video if you have any questions about what was happening, because I know it's really hard to CAD without any explanation for what's actually going on. But today we're going to be continuing from where we left off, and that means we're going to be CADing all the shafts that come out of the gearboxes, the shafts for the wheels, how the sprockets mount, how all the the bearing blocks mount, all that fun stuff. So let's just get right into it. The first thing we want to do is, when we have our drivetrain, is that you want to, I think I mentioned this in 2 videos back, but we know that this bearing block is fixed. It's not going to move, right? But since we're running chain in between this gearbox and the wheel that's going to be here and here, we want to be able to adjust how far that wheel is away from the gearbox, simply because chain is not going to be fixed. As I've mentioned a few times, the chain tolerance is actually pretty significant, and the way we account for this is by using a bearing block. So what we're going to do is we're going to head over to VexPro, and I'm just going to reiterate what a bearing block is so you guys understand. VersaFrame, clamping bearing blocks. So right here in this first picture, they make it very clear about what it is. Basically, all you have is this bearing block, and they don't have it in the picture just to kind of show you how it works, but a bearing sits inside here. And this cam over here, you can adjust this cam, and that adjusts how far away this this whole bearing block is relative to your gearbox. So you can imagine that if there's some chain running between here and here, that chain is constantly going to be pulling in the gearbox or the bearing block towards the gearbox, right? And then we use this cam to push the bearing block outwards until the chain is just perfect. So let's start off with that. Because we're going to need 4 sets of bearing blocks, to make it really easy on ourselves, what we're going to do is we're going to make first an individual assembly that contains the bearing block with the bearings, and then we can just copy paste it. I'm just going to start CADing it so it makes a bit more sense, and you guys can just follow along. So let's take a look at the CAD file. I think we want this first one. Nope, not that one. Possibly this one? No. Yeah, I'm sorry if it seems like I didn't prepare for this video, because I really didn't. I'm just making it just like how I would CAD it during the season. So it looks like Vex is not providing an assembly that I want. They're just providing the raw file of just 1/2 the bearing block, which I guess is okay. So let's go ahead and download that. Open this up in Inventor. When we download parts from Inventor, what we're going to want to do is make sure you're on all files when you're looking at parts, and then just go to date modified and scroll to the top. It should give you everything you need, possibly. Yep, I love this. I love this a lot. First, a block kit, fantastic. So we're going to open this up. Click OK. And the reason we want to open the step file and not just import the step file immediately into here is because when you open it in Inventor first, it converts it to an IPT, as you see here. So that's an Inventor part file. That's what IPT stands for, right? So we're going to do File, we're going to do Save As, and we're going to save it into the same folder that we've already started making all of our other things, which for me is going to be in here. Let's just save it as the part file itself. And now what we want to do is we're going to open and make a new assembly. So let's just make a new assembly. And we're essentially just going to make what's in this picture here, right? Just with a bit more, a little bit more. You'll see what I'm talking about in just a second. So let's open up the VersaBlock kit, put 2 of these back to back. And obviously, since we're starting assembly, the first thing we want to do is change our view mode. So we go to change our visual style to shaded with edges. Immediately you can see a big change in the way these look. It makes it a lot easier. Next thing I want to do is import the bearings into here. So let's go over search of bearings. We're obviously going to be looking at hex shaft bearings because that's what we're going to be using. CAD files. I'm looking at a flange bearing that's 1/2 inch hex. I'm pretty sure this is the one I want. Hello? Alright, so it's not giving me a preview, but just by the description, I think this is what I want. This is pretty standard for FRC. This is what I'm going to be using. Again, before you actually import it, you want to make sure you open the file itself. There we go. And then let's do a file save as right into the folder we're going to be using. Probably should make this a bit easier to access. Great. And now, going back to our assembly, let's just import that. I'm going to use this, basically to rotate this, I'm just right clicking and then I'm following these axes. You can do guess and check, but if you just like look at the axis that it's actually spinning on, it's not too hard to figure out what you need to do to get it to the position you want. So I'm just going to constrain these bearings inside these holes. Sorry if I'm moving a bit fast. There's a lot of content I want to cover in this video. So if there's anything that's unclear, just leave a comment. So constraining axis to axis. Make sure you get not this green dot, but the whole axis itself. Constraining it to this axis here. Same thing on this side. Next thing you want to do is make sure that the flange is on the outside, because that's what's going to happen in real life, right? I'm pivoting like this, clicking this face of the bearing, and doing this face of the bearing block. You can see that it's basically flush with the inside, which is exactly what we want. Looks good to me. Alright. If you remember from our previous tutorial, whenever we start an assembly, you want to ground one of the pieces you're working on and just make all your work centered around that. So I'm going to right click on this, go to grounded. Now I can't move anything besides, I can move everything besides this block, right? Now I'm going to do what you see in this picture, or sorry, what was in the previous picture. This is centered around a piece of VersaFrame, right? And VersaFrame is 1 inch thick, or 1 inch thick. So what we're going to do is we're going to do constraint that puts these two together, but then separates them by 1 inch. So if I look at it like this, you can imagine that there's a piece of VersaFrame running through it like this, right? So I offset it by 1 inch, click apply. And now to align the rest of it, there's a few options I have. I think the fastest way would just be aligning the two axes of the bearing, which works perfectly. And this is the next thing I want to do. Remember, before you're done with the assembly, make sure nothing moves, right? Because if something moves, once you import it into a different assembly, there's no way to guarantee that these are either exactly parallel, if the holes are aligned. You want to make sure that's done before you move on to the next step. So I'm going to constrain these axes. You can pick any two matching holes, it doesn't really matter, but I'm just going to pick these two. Great, nothing moves. These bearings can move because obviously they move in real life. And I'm just going to save this. I can add these bolts, but that's kind of a waste of time. We can get into that later. Alright, let's go ahead and save this assembly. And let's save that as bearing block assembly. Save it one more time and head back to our full West Coast drive. Again, before we start adding stuff to this, we're going to change our view mode to shaded with edges. Just makes stuff a lot easier to see. Also, I don't really like these planes that are sticking out here, so I'm going to go to object visibility and turn off user work planes. There we go, now they're gone. Now let's import our bearing blocks. But before I import the bearing blocks, I need to reiterate what a drop down is. So when we made this, we CADed it with all these two holes at the same level, right? Which is exactly halfway up the VersaFrame. That just makes it very easy to machine. And this one was shifted up, I believe it was shifted up 1/16 of an inch, right? Now, the way these bearing blocks are set up, if you look at the description, let's take a look here. Let's see. Okay, somewhere in the description, they explain how your bearing blocks will, the center of the bearing, if I take a view like this, the center point of this bearing will never be halfway up the VersaFrame. It'll never be an inch away from the bottom edge. It'll always be an inch and a 16th. And the reason they do that is to allow for a center drop. And what I mean by that is, if you look at this piece of VersaFrame right here, the center of that hole of the bearing block itself is shifted down 1/16th. And you need that center drop on West Coast drives simply to allow for easier turning. And that whole design is intentional. That's why this is shifted up a 16th. So when this bearing block is shifted down a 16th, you get an overall center drop of 1/8. If that doesn't make sense, just keep watching the video. It'll make sense a bit later once I start showing you how this all comes together. So let's go ahead and place our bearing blocks. We're just going to do a little rotation to make it look exactly like we want it. So if I line it up like this, you can see how this hole is not lining up with the actual bearing, right? And that's intentional. All we care about is the hex shaft, which is running through the hole. And there's just enough clearance to allow the hex shaft to spin without it contacting this metal edge. But you can clearly see that the hex shaft is actually a 16th down from the center of the hole itself. So let's go ahead and place 2 of these. And let's do a quick rotation for this side. Now let's start constraining this. First thing we're going to do is constrain this face to this face. Actually, I take that back. We're going to go back to selection 1. It'll probably be a bit easier if we do an axial constraint from here to here. Yeah. And then do a face-to-face constraint from here to here like this. Yeah, that'll be a bit easier. And then for the rest of it, I'm pretty sure all we have to do is click this top face and click this top face. So obviously, since it didn't do it automatically, it's going to give you an error. And the reason this is occurring is if you open this up and you actually look at this, or let's inspect this and measure the distance. The distance between this face and this face is not 2 inches, it's 2.005 inches. So it gives you just enough clearance for you to actually put it together in real life. And so basically to allow for this to happen and actually work in CAD, basically all you have to do is, let's see, well, what did I do last time? I think I did planar constraint, I believe. Let's see. So this is part of the learning process, all right? I know I'm making a few mistakes as I go. All right, I already know what I did wrong, and it's real simple. I should have not constrained the axis from here to here, because essentially when I'm doing that, it won't let me actually do the drop down part, right? So that was a mistake on my part. I should have made it how we would have assembled it in real life, which was having the face of this side touch the top, right? Because gravity, you would obviously let the gap happen on the bottom. And that works way better. All right, let's do the same on all of them. So we're going to go axis to axis, right? Then we're going to do, oh, I made the same mistake again. Guys, this is why you should not be like me. I just do a lot of stupid stuff all the time. It's a learning process for everyone here. Face to face, face to face, right? Face to face. And then for this one, you can't see it, so I'm going to move it up first. Click constrain, face to face, right? We're going to do this on this last one. Okay, now to make this whole thing symmetric, what I'm going to do is line up the axes of the opposite bearing blocks. So this bearing is going to line up straight with this one, right? This one with this one, right? So when I slide this side, the other side does the same, which is exactly what I want. Now, the hard part is determining how far away from the gearbox this bearing block is going to be. Because if you remember, this bearing block is not centered with this axis, right? So that means that we can't constrain this axis to this hole. Instead, we have to define how far away this bearing block is going to be from this gearbox, right? Now, right here, I do want to reiterate what this whole center drop business is. So let's bring these a bit closer so you can get a better visual. Now, if we compare these three side by side, it is pretty distinct how this bearing is above this one, and this bearing is also above this one, giving you a total distance between this bearing height and this one, total to be 1/8. So there's a 16th difference, I guess, away from the center line. So none of these bearings are actually an inch away from the VersaFrame's top edge or bottom edge, right? They're all 16th away from the center line. And that gives you a total center drop of 1/8 inch, which you absolutely need for West Coast drives where the wheels are small and you want to avoid scrubbing when you're turning the robot. And that's what the center drop is for. The center drop allows the robot to pivot a lot easier. And you might think that it makes the robot rocky or like tippy or whatever, but it absolutely does not unless you're using really, really big wheels. So you absolutely need this in West Coast drives. Alright, so let's shift this back here and go back to constraining it in this direction. What we're going to do is we're going to take a look at the center distance we chose when we were making this VersaFrame by opening this up, looking at, I believe, this sketch? No. This extrusion. Alright, right here you can see that we chose a center distance of 8.5 inches, right? So we can just exit out of this and go back to an assembly. What we're going to do is we're going to click constrain. In this scenario, we actually do want the green dot because all we're defining is the distance between points and we're not trying to align axes. So we're going to click this green point and this one, and we want the offset to be 8.5 inches, right? There you go. It automatically shifted it. Same situation here. Alright, and then we can see that the VersaFrame is just barely, actually I believe it is going into the gusset itself. We have two options. We can either change the gusset to like make sure it doesn't collide, or, which is probably like more realistic, have like the freshman file the gusset down so it doesn't collide. That's probably what we would do. If you want, you could just adjust the gusset, which I guess would be faster, but don't really have time for that, so freshman can just do it. Alright, let's do the same thing on this side. Center point, 8.5. Okay, it's giving me an error. So let's cancel the operation and try again and try to figure out what we did wrong. Oh, real simple. The issue that it's having is that I already said this is 8.5 inches away from the gearbox, and then I made these two constrained to each other. So it would just be redundant to say that this bearing is going to be 8.5 inches away from this one, right? It's just redundant. Let's do the same thing here. Let's do 8.5. Okay. Again, I'm checking to make sure nothing can move because we wouldn't want anything to move in real life, right? Let's go ahead and save this for now. The next thing we need to add is the actual tensioning part of this, which are the cams. So that cam is going to allow you to essentially shift these bearing blocks around. All we have to do for that is download the CAD and add it into the assembly. One of these should be it. Amazing. None of these provide the actual CAD. There you go. Oh, beautiful. It's a zip file for one part, of course. Let's just extract that boy. Alright. Open it up in Inventor. I love this. Didn't I just extract the file? Yes, I did. It's right in here. There we go. Let's just save that into our folder that we had earlier. Sorry, I keep forgetting what I was using. Alright, going back to the assembly, all we have to do is import this. Very easy. We want to import it or like attach it to the side that would be resisting the chain. So the chain is tied between the gearbox and the shaft here, right? That means there's constant tension going towards the left, and we want to push it towards the right using the cam. So I want one here. I want one here. Same thing on this side. Alright, let's do some constraining. We're going to do axial constraints like this. I'm just going to go through this really fast so we can move on to the next part, which is actually a lot more important. Alright, and then face-to-face constraints. If you care enough, you can just adjust this to the minimum length. So that's what it would be in real life, right? It'd just be in that indent. That's if your chain was absolutely perfect. It's most likely not going to be like that. But we're going to go ahead and attach it like this. Same situation on this side. Why don't we just pull these out and then do face-to-face constraint. Alright, let's save this and move on to the next part, the fun stuff, sprockets and wheels. So these are the last components that are going to be part of our drivetrain. So if we look at this drivetrain, we need a sprocket on this wheel and this wheel, right? The thing is, I can't just put one singular sprocket here and here, because you can't just have one chain length running the whole thing, because what's going to end up happening is that that chain length is just going to bounce off the sprocket in the middle and go straight to the one here because of the center drop. What we actually need is a sprocket that goes from here to here, right? And then another sprocket that connects from here to here, right? And so that allows for, it actually allows for two things. It allows for making sure that that chain doesn't bounce from here to here. And it also makes sure that if there's chain failure on this side, we can still make sure that this center wheel is being powered. So I know that doesn't actually make too much sense right now, but once we import the sprockets, it'll make a lot more sense. So let's go ahead and just get right to that. You know what? Just to make this a bit easier to understand, let me just give you a brief overview of the drivetrain that I'm imitating this off of, and I think you guys will get a much better visual. So if we look at the West Coast drive here, let's zoom in real quick. You can see that they're running chain from the gearbox to here, and then a secondary one from here to the end. Now the problem in this situation is that I only have one singular sprocket in here, and so I can't do the setup that they have in here, but this is the most ideal scenario. I don't want to go back and add another sprocket to this, because that's just going to be a waste of time for this video. But you guys can see what I'm saying is that if there's a chain failure here, this last wheel will still be powered and your drivetrain will still work. And if there's a chain failure here, this chain will still be powered and still be working, right? That's essentially what we're going for. But can't really do that here because we only have one sprocket. Even if I did add another sprocket, these motors would probably run into each other. So in that scenario, you would just need a wider wheelbase in the first place to make that work. Anyways, let's move on. So getting the sprocket. Let's go back to VexPro and take a look at the sprockets we need. I'm going to open this up and take a look at the sprocket I already have in here. I believe it's a 16 tooth number 25 sprocket. Let's see, the part number is 2642. So if we take a look at the sprockets that are here, I'm going to just do Control F 2642, and apparently it does not exist. Oh, that's because I'm on number 35 sprockets. What we actually want is the number 25 sprocket, which would be here. Let's do Control F 2642, 16 tooth, right? So we need to download more of these and add it to our assembly. I'm going to the CAD files. We're going to look for 2642, 2642. Right here, 2642. Let's just download this. Open this up. So I could just copy paste this, but I don't know where it's pulling this file from. So I'm just gonna resave it into my new like drivetrain folder, if that makes any sense. Alright, let's do save as. We're going to go back here. You can obviously color the sprocket to be the way you want, but we're going to leave it gray for now. Alrighty, let's place that sprocket right into here in the orientation we want. Let's just imitate the orientation we have, and actually, there is a strong possibility that we can get away with facing the other way, which allows us to do something else, possibly. So we can't do that because if I overlay just the sprockets on here, you can clearly see that the sprocket is going inside the VersaFrame, which would not be possible in real life. So we're gonna go the other way. Here. Right, and now we need another sprocket going to this side, so let's place another sprocket here, and then we're going to make this stick out on this side like this, right? This is actually not the most ideal way to do this. There's definitely a different way that I would approach this in hindsight. I would have definitely taken the approach that I showed you earlier on 254's website, where they set up a double sprocket inside here. That makes it a lot more compact down the line here, because now I just have a lot of space here, right? But that's okay for now. Let's just move on. So chain obviously needs to be aligned between the two sprockets. So what I'm going to do is I'm going to do what we have called a flush constraint between the face of this sprocket here and then this sprocket here, right? And if we bring these two together, you can see that they're going to be perfectly aligned, like in this direction. That means their chain is going to run in between them perfectly. Next thing you want to do is line up the actual center or the axes of the sprocket and the bearing. So just click the axes here, select the axes here. There we go. Nothing else can move, which is just the way I want it. Now, situation on this side, I want this face attached to this face, right? And then this axis attached to this axis. And then, so I have chain running in between this sprocket and this sprocket, right? Now I want chain running between this sprocket and this sprocket. So we're going to do another flush constraint in between this face and this face, right? And then switch back to mate for your axis constraint that's here and here. Cool. Now we have nothing else to worry about. I'm not going to repeat the process on this side just to save time, but you guys get the idea of how chain is going to run in between this sprocket and this one, and then this one and this one, right? Now, second to last thing, we need to add our wheels, and then the final component of this whole thing will be adding shafts, right? What we're going to do is we're going to go over to VexPro. we have a few options for what we want to do with wheels. I think in our JVN design calculator we were going for 4-inch wheels, so that's what we're going to be using on here. 4-inch is pretty standard. Teams can sometimes go down just for smaller wheel sizes for less tippiness, but I think 4-inch wheels is the standard. I actually don't want traction wheels. I actually want Coulson wheels. Let's see, Coulson hubs. Hello, Coulson Performa. Yeah. So these wheels are really nice because they're very durable. The problem is that they wear out really, I wouldn't say very quickly, but after one competition, you do want to replace these wheels because they can mess up with their coating because their diameters wear down really fast. So let's look at their CAD files. We want Coulson Performa 4 inches, right? I don't want the 0.8751 just because of how skinny it is. The 1.51 seems pretty good. I don't want the 2-inch one because 2 inches would extend like way out here. That's too thick. So this is the one I want, 4 inches by 1.5 in thickness, 1/2-inch hex bore. That seems pretty good. Let's download that, open it up in Inventor. And then save it right into our assembly. God, I need to organize these files. Alright, let's go back into here. Let's place our Coulson Performa wheel. We obviously want 3 of them. We're going to start by constraining the axes, which is pretty easy. Grab your axes here. You can basically click on anything here that defines the axes. I think I'll go with this. Alright, let's do the same for all of them. Pretty simple stuff if you've been following the other tutorials. Now, next thing you want to do is line up the faces. So we're going to be looking at as the most outer face of the wheel. And that's going to be, as you can see, this right here. So I'm just going to pivot slowly and take a look at what that is. Alright, that sounds cool. Click that face and match it up with the most outer face here, which is probably this black box. Let's take a look. Yep, that seems good. Alright, let's do the same thing on the other ones. I believe that's the most outer face. Let's redo that. Take top view. Yep, that actually is. Got lucky there. Outer face, right? Same thing here. Outer face, outer face. Now everything is lined up, nothing is moving, everything looks the way it should be. I'm just going to take a quick side view to see what we have here. You can see this wheel is dropped below this one and this one, making for a pretty good center drop. Now the last component of this before we finish off this video is adding the shafts. So shafts is going to be the axis that all of these turn on, right? The first part we want to start with is the shaft that goes from this gearbox to the outside of this wheel. And to figure out the length of the shaft, all we have to do is figure out the distance from this outside face of the wheel to the very back of the gearbox, right? So let's measure this from the outside here. So we're not measuring from this edge because the shaft really only has to end here. We don't need anything more than that. Let's go from here to here. 4.962 inches. That's kind of an odd number. So if we were going to machine this in real life, probably just do 5 inches. But for the sake of CAD, let's just copy this number. What I mean by that is that in CAD, we'd make it 4.962 inches, and then in real life, once we get to the actual fabrication part, you'd probably tell your fabrication students, hey, make a 5-inch long shaft, and then if necessary, file it down just a bit to make it flush, right? So let's make a new part. We're going to make a hex shaft, so 6-sided, polygon, escape, dimension from here to here. Click that, and then we're going to type in 0.5. If you want to get really fancy, I'm only going to show you guys this once. We're going to make it thunder hex, which is 0.5414. delete these two dimensions because Inventor is wacky and won't let you do it otherwise. Trim off this excess part. This is really extra. You don't really need to do this, but you know, for the aesthetic. Alright, and then I'm going to add a 0.25 inch hole in the middle because that's how Thunderhex is sold. If you guys don't believe me, just go ahead and look up Thunderhex and see how they sell it. There we go. That's your Thunderhex. And now we're going to finish the sketch and extrude it to the length, which I believe was 4.962. I think that was the length. We're going to go with that for now. Now, the thing about the gearbox shaft is that the back of it is going to a round bearing. And so you could make that a hex bearing, and to retain the shaft, you could either do a C-clip or a bolt and washer, but doing a round bearing is essentially the same thing as long as the flange is on the inside, because if the bearing tries to come out, it physically can't because the hex shaft is bigger than the circle and the flange is on the inside, right? So in order to like pull it out, it would have to rip out these standoffs, which it obviously can't do. But what we're going to do is round off the end of the shaft. And I did this in a previous episode, but we're just going to reiterate that. So I'm going to do a sketch on here. I'm going to do, what is it? What is the inside of it? I think it's like 0. I don't remember. We're just going to take a look at it. We're just going to do a quick inspect. It's probably something really stupid, like, yeah, 0.5 inches. Go back here, 0.5 inches, right? And then make one circle that's just any size bigger than the whole hex shaft. And then we're going to extrude it back 0.313 inches. Where did I get 0.313 inches? Well, there's two ways to calculate this. Fastest way would be just to open up this bearing and see how thick it is. And if you do a quick measurement from here to here, you can see that it's clearly 0.313 inches. Another way, if you want to do some quick mental math, this plate is a 1/4 inch thick. The flange is 16 inch thick. A 16th plus a 1/4 is 0.3125, which is approximately 0.313 inches, which gives you a total thing of that, right? Makes sense. Shouldn't be that bad. Let's save this, add it to a gearbox. I'm actually going to save it to a folder for the gearbox, just because that makes more sense. Yeah, cool. Now I'm going to add it to this full assembly here. Okay. Axial constraint here and here. It's getting really hard to see stuff, so I'm going to go to the view and change the visual style to shaded with edges. Go back to assemble, hit constraint. Let's do a flush constraint with the back here. Flush constraint right like that. Okay, and now just to confirm everything's the proper length, let's save this. Go to West Coast Drive Assembly and see how far it sticks out. It should be flush with the wheel, which it is. Looks like it's just flush. Now, in order to retain the wheel, or what we'd basically do, I am going to add this to the CAD later, but I won't in this video just because it's kind of a waste of time. What we'd basically do is thread the inside of the shaft, and then once it's threaded, you put in a bolt and washer. So the washer, you know what? I'm just going to do it, or I'm not going to do it, but I'm going to give you a quick example just to show you guys what I'm talking about. Let's see here. We're going to take a look at our actual robot. Let's see here. Can we go to drivetrain? Do we have drivetrain? Yes. Alright, let's open up this boy. This big boy assembly. Let's give you a brief overview of what is going on, what the final product is trying to look like, right? Let's turn off the visibility. I just right click, turn off visibility. Right here, this is shaded with edges. This is what I'm talking about. So there's no washer in this CAD. That's kind of useless. Maybe it's on the other side. Alright, so I guess I just failed to put in the washer, but you can think about it this way. this bolt is not going to come out of the shaft, right? So if this bolt is sandwiching like a big washer in between the wheel and the bolt head, that wheel is not going to slide off the shaft, if that makes any sense. And that goes, oh, maybe I did it on the inside. But it's the same situation on the inside, right? We're going to have a bolt and washer on the inside of this. You can see the threads here in the shaft, and that's going to retain the sprocket. So I hope that makes a bit more sense. If you guys want me to clear that up, please just drop a comment. And this is essentially the same process for this and this. We're going to have two different shaft lengths, obviously. Actually, they're not two different shaft lengths. These two shaft lengths are going to be the exact same since the sprockets go out the exact same amount. That's going to be the last thing I do for this video, so let's just quickly do that. What I'm going to do is measure the distance from the outside of the wheel and the outside of the sprocket. And that's going to be the shaft length we make, 4.202. So now instead of making the part all over again, what I can do is go to the shaft I made here. Let's do a file save as. And so that's just going to create a new file part. And we can call it, let's call it, I don't know, other axial. You can name it anything you want as long as it's descriptive. So since I did a save as, it didn't mess with what we have here. That shaft still exists, but now I have like another copy of it. So the first thing I'm going to do is delete this because we don't need that rounded end for the other one. And all I have to do is change this length, which was 4.202. Again, if we were machining this in real life, I'd probably just ask the fabrication students to make this a 4.2-inch long shaft, right? So hit OK. Save this one more time. Go back to our assembly. Import this. So assemble, place. Head over to right here. Rotate, right click, rotate, place to. Escape, constrain the axes like this. And then constraint, just do a flush constraint from the end to end like that. Check on the other side to make sure that it is flush, which it is. And then all we have to do is the same process here. Oh, I can't click that because it needs to be a mate constraint. So I'm going to go back to 1, mate, axes, or not axes, axis, apply. Let's do a flush constraint from here to here. Alright, so there we go. Those are all like the main moving components of the drivetrain. For sure, if you're making this in like an actual like FRC competition setting, if it's build season and you're in week 1, you're designing a drivetrain, you absolutely need to CAD the bolts and the washers to make sure that doesn't interfere with, for example, either frame perimeter rules or like the bumpers and the way they mount themselves, or anything that's like on the inside of your frame. You need to CAD the bolts for sure, because you never know what unexpected issues might arise if you're making this in real life. So you absolutely need to CAD the bolts. But that's all I'm going to do for today. In the next video, I'm going to get into how to create bumper mounts or possibly how to make the belly pan. So stay tuned for that. Thank you guys so much.